All right, let's tackle a classic problem from I.E. Irodov's famous physics collection, problem 1.53. It's a fantastic puzzle about bouncing cubes, compressed springs, and the exact moment everything decides to jump into the air. Let's dive right in. So here's how we're going to approach this. We'll break it down into 5 clear, logical steps. Think of it as our roadmap to get us straight to the solution without getting lost.
First things first, let's really get a handle on what the puzzle is asking. In any physics problem, really visualizing the setup and understanding the goal is, without a doubt, the most important first step.
So try to picture this in your head. You've got 2 identical cubes. One is just sitting on the ground, and the other's on top of it. Sandwiched between them is a spring that's been squished down, just full of potential energy. And the only thing keeping it all together is a single thread.
So what's our mission here? Well, it's a two-parter. First, how much do we have to squish that spring so that when it expands, it eventually pulls the bottom cube right off the ground? And second, if we're given a specific compression, how high does the whole system's center of mass, its average position, actually go?
Now hold on. Before we just start scribbling down equations, it's always a smart move to step back and think about our strategy. Let's lay out the tools from our physics toolkit that we'll need for this job.
And why do we do this? Well, it stops us from just, grabbing formulas at random and hoping one of them sticks. We're going to be deliberate here and pick the right tools from the start. And it turns out, these 3 big ideas right here, they're literally all we need to crack this thing open. We'll use force analysis for that liftoff moment, we'll use energy conservation to see where the energy goes, and we'll use the center of mass to describe the whole system once it's flying.
Okay, let's dive into part A. The goal here is simple. Find the bare minimum spring compression, that delta L, that's going to make the bottom cube actually jump.
Let's walk through what happens, moment by moment. The thread burns, and whoosh, all that stored energy launches the top cube upwards. As it flies up, it starts stretching the spring. And here's the key idea. That bottom cube will only lift off if the spring stretches enough to yank it upward. So, put yourself in the shoes of that bottom cube. What's holding it down? Gravity, right? Its own weight, mg, is pulling it down. So what on earth could possibly pull it up and make it jump? And boom, that's the heart of part A. It's just a simple force comparison, a tug-of-war. For that bottom cube to lift off, the upward pull from that stretched spring has to be stronger than the downward pull of gravity. The spring has to win, period. Okay, so the big question is, how much does that spring actually stretch? And for that, we turn to our trusty friend, the law of conservation of energy. We're just going to focus on the top cube for a second. The energy it started with in the compressed spring gets converted into height and into stretching the spring. So we're basically saying that all the energy we crammed into the spring at the very beginning has to go somewhere. It turns into the cube's height, that's gravitational potential energy, and whatever energy is left in the spring as it stretches. Solving that little puzzle gives us the max height, y, and that tells us exactly how much the spring stretched. And this is where it all comes together. We take that amount of stretch we just calculated and we plug it right back into our rule for liftoff, the one that says the spring force, k times its stretch, has to beat the cube's weight, mg. After a little algebra, we get our final answer. Awesome! Part A is done. Now for the second part. This time, we're given a specific amount of compression, and we've got to find how high the whole system flies. So the problem hands us a specific number for this part, 7 mg over k. Now, the very first thing a good physicist does is a quick sanity check. Remember our result from part A? We said liftoff happens if the compression is more than 3 mg over k. Well, 7 is definitely bigger than 3, so we know for a fact this system is going airborne.
So what's our game plan? We're going to split the motion into 2 clean stages. First, what's happening at the exact instant of liftoff? What's its height and speed? And second, once it's in the air, how much higher does it coast, like a simple projectile?
So our first task is to figure out the launch speed, not just of the top cube, but of the whole system center of mass. We can do this using energy conservation again. Right at that liftoff moment, the bottom cube isn't moving yet, but the top one is. That lets us calculate the overall speed of the system as it leaves the ground. And this is such a cool and powerful trick in physics. Once both cubes are off the ground, you can pretty much ignore the complicated spring bouncing around inside. You just treat the system's center of mass as if it's a single ball that you've tossed straight up into the air. It simplifies things beautifully. All right, we've done the heavy lifting.
let's put all the pieces together and take a look at our final answers.
And there you have it, the two clean answers. For part A, to make it jump, you need to compress that spring by an amount greater than 3 mg/K. For part B, with that specific compression they gave us, the whole system's center of gravity will rise to a maximum height of 8 mg/K.
But look, the formulas are great, but they're not really the main point. The real insight here is seeing how these huge ideas in physics, force, energy, center of mass, aren't just separate chapters in a book. They're all parts of a single, elegant language we use to describe what's happening.
And I'll leave you with this to chew on. We solved this problem in the perfect, clean world of a textbook. But what happens when you bring it into our messy, real world? How would something like air resistance, a force that drains energy, change our neat and tidy answers? Something to think about.